Can you see it now?
See.
Good. So we have the short lesson today. I hope I'll survive because I have a little fever from the vaccine. It's not a very light thing. Anyway, I hope you can hear me. Okay, so let me just recap 1 second. So we had seen the importance of deriving the fundamental equation in terms of, for example, the internal energy as a function of S, V, and N. But really, using the concept of Legendre transforms, we can essentially derive completely equivalent forms of the fundamental equation. Okay, completely equivalent forms. We have seen that the Legendre transform is essentially an equivalent representation of a function like u of s in terms of its intercept on the y-axis essentially, and the gradient, okay, the slope tangent to that curve. And with this trick, we can really derive a number of equivalent so-called thermodynamic potentials. For example, here, still in the plane US, okay, this is the Legendre transform of U, and it's U minus du ds times S. Clearly, we know that du ds, if you look back in the notes in the slides, is equal to T. And here it is, automatically we have Helmholtz potential. So I'm not really making sort of a leap of faith in telling you, okay, this is Helmholtz potential. Why is it like that? Well, it's simply the Legendre transform of U. And equivalently, we can do all sorts of transforms. Most importantly, for example, we can derive enthalpy, okay? Again, I'm letting people in. Please be on time. And it turns out that, well, now we're in a different plane. You see that the slope now is as a function of V, not of S anymore. Du by dV is actually the pressure, okay, with a minus sign. So the enthalpy ends up being U plus PV, okay? If you also take the differential of this, of dH, okay? And you substitute for du, eventually you get the actual expression for the differential of the enthalpy. So from this here, you can derive more or less two things. One is its meaning, okay? For example, at constant pressure, let me see if I can manage to. At constant pressure, this is 0, okay? And for a closed system, dN I is 0, okay? So at constant pressure and for a closed system, clearly the enthalpy is nothing else but the heat exchanged, okay? dQ equals T ds. Not only that, but we can rewrite it in the form, it's a perfect differential. I don't know why I can't write anymore with this thing. So this would be dH well, give me a second here. There must be a better way. Wait a minute. Yes. Okay, so on and so forth. No, don't let me write the whole thing, but obviously this is a constant pressure and a constant number of moles. times ds, okay, plus dH by dP, dP plus, and this would be dH by dNi, dNi times dNi, okay? It will get better. My handwriting will get better for sure. I don't know why it's, it also seems a little stretched, doesn't it? Well, whatever. Anyway, so these derivatives here acquire meaning, of course, because this is temperature, clearly, this is volume, okay, and this is mu I, so the chemical potential. And for each of those thermodynamic potential, okay, I can derive these. I won't do it for the Helmholtz potential. It's boring. I mean, I don't want to put too much confusion into, but these we're going to probably be using, okay? And so for each of those chemical potentials, you'll be able to define essentially these intensive, okay, quantities, which are essentially the derivatives, okay, with respect to extensive quantities. I mean, extensive and intensive quantities. So, for example, T is when you divide two extensive, and here, for example, an extensive divided by an intensive quantity, still an extensive quantity. Now, we can go on forever and derive all sorts of chemical potentials, but really the most important one that we'll be using is Gibbs energy. Okay, so let me just derive it very quickly, because clearly Gibbs energy is one of those chemical potentials, or Gibbs potential is one of those chemical potentials that have a direct application to chemical systems and chemical reactive systems. Okay, so as exactly like we did before, we start from the fundamental equations in terms of internal energy, so S, V, and N. Okay, and essentially we define the Legendre transfer, which we call, for example, G, okay, as a function. So remember here what we're doing of the slopes in the plane S and V. So essentially here we have du by ds, okay, and du by dv. So it's a double transformation. It's not on one plane, okay, but it's more like on two planes, okay, on a 3D sort of space. Clearly, if you remember going back to the notes, this will be temperature, okay, and this will be the pressure with a minus sign, okay? So recalling the definition of the Legendre transform, okay, which we call, in this case, G, it's U, okay, minus, so this is essentially the equation of the intercept, which comes directly from the equation of the tangent line. In this case, it's multidimensional, so we have du by ds times s, okay, and du by dv, okay, times v. So long story short, this is where we derive the form, okay, of the Gibbs potential. Again, I could have given it to you as a definition, but then clearly we wouldn't have really understood why the Gibbs potential comes in this strange form. Okay, but now again, as a Legendre transformation, we understood why it is. You can take the differential of this, okay, dg. You can do it as an exercise by substituting the differential of du. So there's some cancellations. At the end of the day, you get something like this, minus s dt. Why can I write a little better? Oh, God. Do you have any idea why I'm not? Maybe. I've done an entire course from September to December, and then it seems that now I've completely forgotten how this thing works. Anyway, VDP, okay? I'm just skipping a few steps because I couldn't care less to do the whole thing, but believe me, this is what you get at the end. dn. So from the differential, you also can establish the meaning of dg, of what dg really is, in the sense that for a system that is, for example, at t equals constant and p equals constant, okay, these two terms are 0, okay? So all we have left is this term here, okay? And what this is usually addressed as is useful energy. Remember that whenever we have an equilibrium condition, clearly dg equals 0, ds is a maximum, so ds is 0. So we can't really extract anything else from the system, right? Because everything is at equilibrium. But in this particular case, when dg is different from 0, this assumes the meaning of a useful energy that can be extracted. But it can be extracted by virtue of what? Of the change in composition. So through essentially chemical reactions at constant temperature and pressure. Okay? This is why the Gibbs energy potential is really the most used in chemistry, simply because in an experimental setting, we're usually in these conditions of constant temperature and pressure. I can, for example, have a chemical reactor, which is open to the atmosphere, so it operates at constant pressure, for example, and I subtract heat, okay, so that I'll keep it at the same temperature. That's essentially a situation that is far more, let's say, familiar in a laboratory setting than keeping, for example, the system isentropic or isolated, okay? So we're going to be dealing a lot with Gibbs energy. Again, as we did with the enthalpy, you can derive, well, the fact that these derivatives, dg by dt, okay, here is equal to a constant, obviously, pressure and number of moles is equal to minus s, okay, and so on and so forth. So you can do all sorts of things and derive all sorts of derivatives. We're going to be needing a few of those later on, okay? So you don't have to remember them clearly, but you can always derive them. So this in V obviously is dg by dp, okay, at constant temperature and number of moles, so that's V, okay? And in this case here, you would have dg by dni, okay, at constant temperature and pressure, and that is the chemical potential. In fact, this is one of the most important definitions, okay, that we can have of the chemical potential, okay? Okay. We're going to see it later on, but this is the definition that we're going to be using, okay? And it's essentially chemical potential mu of I is essentially the Gibbs, it's called the partial molar Gibbs energy, okay? So essentially, it's the increase of Gibbs energy in virtue or by virtue of an increase of 1 mole of one substance, okay, in a mixture. Okay, we're going to define what a mixture is later on, but keep in mind that we can really define all sorts of chemical potentials and their derivatives, okay? Now, each of those, as I said the other day, is useful in particular circumstances. For example, the Gibbs energy is particularly useful when you have things like temperature and pressure kept constant. In fact, let's go back now to the concept of equilibrium. And I'd like to play a little bit around with the conditions of equilibrium that we have derived, okay? So remember that we've derived them for a composite system, okay? So we have an isolated composite system. So this is an isolated system, okay? And this is the internal constraint, okay? This is the internal constraint, which can be, for example, an adiabatic wall, a rigid wall, or an impermeable wall of some kind that we can manipulate between essentially these subsystems 1 and 2. Okay? And we said that if we remove the internal constraint, for example, if 1 and 2 are at different temperature, we remove the adiabaticity, for example, the system, the overall isolated system, will reach an equilibrium state where essentially the entropy is maximized. So our equilibrium condition is one of maximum entropy at constant internal energy, because this is clearly isolated, okay? So essentially ds equals 0, okay? So we can try and play around with this a little bit just to see what the consequences are. So again, let's go back to our composite system. Well, the entropy of this, in order to maximize it, we have to write it, okay, the entropy. So the entropy, clearly, it's a composite system, so it's the sum of system 1 and system 2, right? Subsystem 1 and system 2. Well, entropy is extensive, so it's additive over constituent subsystems, okay? So, for example, suppose that this wall here is, for example, rigid and impermeable, okay? So it won't let any volume change or any mass through, but it will let some heat through, okay? So it's a diathermal wall, okay? So because we have to impose ds equals 0, let's calculate ds, which is essentially ds1 plus ds2, right? And, well, we're keeping essentially the volume and the number of moles constant, okay? Clearly, S is a function of U, V, and N, okay? So we can write it very simply as ds by du, so we're only dealing with variations in internal energy, okay, for system 1, okay, du1, oops, and this is the first term, ds1, and ds2 would simply be ds2, ds2 by du2, okay? And if you remember, ds by du is 1 over the temperature. So we have temperature 1 here, and this is 1 over the temperature 2. Okay. So I can rewrite this as 1 over the temperature 1, du1. I forget the brackets, it's a stupid notation, plus 1 over T2. Well, this looks like squared, so yeah, let's put it back. du2, okay? That's our ds, but we have to place the 0 at equilibrium. Let's see what we can understand about this. First of all, remember, this is an isolated system, okay? What does it mean? It means that U, which is, again, the sum of U1 of subsystem 1 and U2, is constant. So first of all, I can say something about du, because du is du1 plus du2 is equal to 0. So essentially, I can substitute for du2 minus du1. So what happens is essentially any loss of internal energy in subsystem 1 is actually the gain of internal energy of subsystem 2. So again, ds, we eliminate du2, and we have essentially 1 over T1 minus 1 over T2, okay, times du1. So how is this useful? So we said that for an isolated composite system like this, okay, ds equals 0 is the condition of equilibrium. Well, we have rewritten now for a diathermal wall, here, a diathermal wall, we have rewritten ds as this expression here. So there's one interesting aspect that we immediately find, that in order for the system to be in equilibrium, so ds maximum, ds equals 0, so the entropy maximum, you have to have uniformity of temperature. It implies that T1 must be equal to T2. So equilibrium kind of implies that any sort of field of intensive variables such as the temperature is uniform. And this is an obvious fact of life. I mean, if this is hot and this is cold, we remove the constraint that keeps them from exchanging heat, and the hot and the cold will uniform themselves to some sort of average temperature, okay? But it gets even a little bit more interesting, because look, suppose that we are at equilibrium. So ds equals to 0, the temperatures are the same, right? Now, if I perturb the system and I displace it ever so slightly from the equilibrium, okay? So suppose I perturb the system. So for example, I make T1 larger than T2, okay? T1 is hotter than T2, okay? Don't ask me how I did it, you know, I have perturbed the system somehow. I took a packet of energy and put it here. What happened is that we have somehow reduced the entropy, and the entropy, therefore, or the system rather, will respond, let's say, spontaneously, so that the entropy will increase back to 0, okay? So if I write ds, okay, the response of the system to the perturbation is the following. ds must be larger than 0. So we have an increase of entropy back to the maximum point. So you perturb the system from equilibrium, you reduce the entropy, okay, somehow, now the system will respond spontaneously to go back so that it goes back to the system. Now, again, I perturb the system so that T1 is bigger than T2. So this quantity here is negative, right? Because clearly T1 is bigger than T2, so this is smaller than this. So in order for this to be positive, so for the entropy to increase, you see DU1, the variation of internal energy of the subsystem 1, must be itself negative. So look what happens now. I make this hotter than this, so T1 is bigger than T2, and the system responds by letting DU1 negative. So subsystem 1 will lose internal energy in favor of 2, okay? So that essentially the two temperatures will get back to being the same temperature, okay? So the system essentially, so heat will flow spontaneously from the hotter to the colder, okay? This is what we wrote down here, okay? And we can do it quite easily, okay? We can play around with this concept, including, for example, not just a diathermal wall, so exchanges of heat, okay? But for example, you can think of this wall, okay, as being also permeable, for example, okay? So now you can have a substance, okay, move from 1 to 2, okay, from subsystem 1 to subsystem 2. And, well, again, you can see it in the notes. Don't let me, because otherwise it's going to last forever, but it's very easy, okay, to determine ds in this general case where the wall is also permeable, not just diathermal, but permeable. So the first term is still this one. So I can write it again, 1 over T1 minus 1 over T2, okay? du1. And essentially there is another term here, okay? Because we are allowing matter, so number of moles essentially, to change in 1 and 2, for example, for a certain species, K, it's easy to show that this second term is will look something like this. You can find it in the notes. We use exactly the same procedure here. But what I would like to do is get to the actual substance, to the actual point, and not waste time with the actual algebra. So you see that we have, instead of a difference of temperatures here, we have a difference of the combination of chemical potentials. Sorry, this is 2, and temperatures. Okay, and this is dn1. Okay, so we are only considering one species, K, and just as we did with the internal energy here, you can say that dnk1 is minus dnk2, because whatever subsystem 1 loses, subsystem 2 will gain. Okay, so clearly the whole thing is impermeable, so you're not destroying matter. But what you see here is something very similar. So at equilibrium, not only do you have uniformity of temperatures, okay, but also of chemical potentials, okay? So essentially at equilibrium, you don't have sort of gradients of anything, okay? that you have complete uniformity of both temperature, chemical potentials. And in fact, we could even do it with pressure, and it would tell us the same kind of thing. Okay, which is nice, because this is what we know about equilibrium. Okay, the absence of differences in intensive quantities, such as temperature, such as chemical potential, such as pressure. Okay. We can do something, the same kind of reasoning that we did for the temperatures. Suppose that T1 and T2 are the same. So the temperatures are in equilibrium. We can rewrite ds, okay, as essentially, we take the T1 out, okay, and we have the differences here of chemical potentials between 1 and 2. Okay. So let's do something similar to what we did before. Let's perturb the system. Okay. At equilibrium, we know that this is 0. Okay. ds is 0. Now let's perturb the system so that, and so if it's 0, clearly the chemical potentials in 1 and 2 are the same. So the same species will be in subsystem 1 and subsystem 2 with the same kind of chemical potential. So there, in a way, there will be no preferential chemical direction, okay, whereby the species K will want to transform itself from 1 to 2 or from 2 to 1, because everything is uniform. Okay. Now suppose that we perturb the system. So we have the species K, okay, in subsystem 1 having a chemical potential that is bigger than the one it has in subsystem 2. Okay, so this term here is obviously negative because there's a minus sign. Now we have perturbed this, so this is positive because mu1 is bigger than mu2. We have perturbed this, so this is positive. So now that we know that the system will respond as a result of the perturbation to increase, okay, the entropy, so that it will reach back to the maximum of entropy. So you see that clearly this term here must be, so this is negative, must be negative, right? What does that mean? Well, you see, I have in subsystem 1, I have increased the chemical potential, and the system now responds so that there is a net flux of matter from 1 to 2. Okay? So what this is saying is that a chemical species, okay, will tend spontaneously to attain, okay, a chemical potential that is lower, okay? Or better still, from a state where the chemical potential is high to a state where the chemical potential is low, okay? So matter is transformed, okay, from a state of high to a state of low chemical potential. And this is more or less the whole point behind chemical reactions, and we're going to see this. So what you should when you look at this thing, what you should think of is essentially, you should think of chemical potentials as being intensive quantities which have the same dignity, okay, of a field of temperature. Only that when you have variable temperature, we know that it's more intuitive to know that the temperature is going to get uniform, but it's exactly the same thing when you have a species, okay, and you have a gradient of chemical potential. Well, this will tend to settle. Whether it's mixing, for example, whether it's actually reacting with other species, okay? But of course, this is less intuitive, so as we proceed, this is going to become increasingly clear. So why did we do this? Simply because to make the point that this is not just a statement. This is really applicable. Okay, you can hear me, right?
Yes, Professor.
Yes. Okay, good. Thank God. The equilibrium condition for an isolated system, like the maximum of entropy, is really something that you can actually apply, okay, to a system. And we derive essentially all of the intuitive conclusions that we know, okay, that a system should behave spontaneously, for example, so that heat flows from the hot to the cold subsystem. Okay. Now we have very few a few minutes left, so I won't have time to do a lot. But bear in mind that we did this for an isolated system. Okay, this is an isolated system. Okay, this only holds for an isolated system. What if I want to apply a concept of equilibrium or a condition of equilibrium, but to a different kind of system? A system, for example, that is not isolated, but it's a constant pressure, or that it's a constant pressure and temperature. Okay? What I would like to know essentially is, how do these conditions of equilibrium change? And really, we have done it already. I mean, we have seen it already by defining the chemical potentials. Okay? By defining, for example, the Gibbs energy, we realize that this essentially, dG equals 0, you will have it for a constant temperature and pressure and isolated and enclosed system. So I have a closed system kept at constant temperature and pressure. dG equals 0 will be an equivalent equilibrium condition than saying essentially the minimum of internal energy. Okay. The only thing is, the advantage of this is that it will be specialized to a particular system. So we will still use these concepts, okay, of isolated composite systems, but in a completely different, well, in a slightly different way. So I have really a few minutes. So let me introduce the concept of reservoir. I'm only going to do it very briefly. So here. So I introduce a special kind of composite system, okay, which is more or less like this. I have an infinitely large, or if not infinite, very large, okay, system here, which is which is surrounded by walls, okay, and it's characterized by a value of entropy, a value of volume, and of composition. And I just put here a superscript R to underline the fact that this is the reservoir conditions, okay, or conditions that are corresponding to this big system here, which is a reservoir, okay. So it's in a sense an infinite composite system. Then I have a much smaller system here. So to have a composite system, you need to have two system, which is, you see, it's contained. Okay, I'll put it here with other kinds of walls. And this is our system of interest. What do I mean by that? I mean, this is the system for which I want to derive, which I keep, for example, a constant pressure, okay? And I want to derive for that system, a constant pressure, a condition of equilibrium, okay? So we are going to call the equivalent values of S V and N K or something, okay? Simply S, V, and N, okay? So this is the system of interest, or we can say inner system, okay? And this is the reservoir. And the whole thing, okay, is the overall composite system. Oops, system, okay? So it's very similar to what we've done so far, okay? The only difference is that it's a little trick, okay? We're not considering an isolated composite system. We're considering a reservoir kind of system where the outer walls, instead of being isolated, okay, instead of not exchanging internal energy, are in fact isentropic, okay? And obviously rigid, so we don't exchange any work, okay? And impermeable. Impermeable. What does this mean? It means that this is an overall system, a composite system that is isentropic. And if you remember, for an isentropic composite system, the condition of equilibrium is the minimum of internal energy at constant entropy, okay? So that's, so du equals 0. Now, for this system here, how do we write du equals 0? Well, we have to take into consideration the value of the internal energy of the reservoir and of the internal system, the inner system, okay? That's it, okay? So, before, let me repeat, in this kind of system, we used the maximum of entropy because it was isolated. Now I'm using a little trick here. And the concept of this huge reservoir, you'll see why in a second. It's just a little trick, okay? And I'll apply the minimum of internal energy. So I hope this, so clearly, because it's additive over constituent subsystems, you have UR plus U, okay? Now, the idea here, I'll do it next time, okay, is essentially to derive, to write down an expression for UR, okay, and depending on what kind of system this is, okay, I will essentially derive a totally equivalent condition to this, a totally equivalent equilibrium condition equivalent to this, okay? Specialized for this particular system of interest. So, for example, I'll anticipate a few things. If I want to keep this internal system at constant pressure, it will be easy to see that this thing will reduce to, okay, essentially a minimum of enthalpy, okay? If I want to keep this at constant pressure and temperature, okay, this will translate to a minimum of Gibbs energy, okay? And this, again, I'll be very quick and underline this, will be the first step, especially for the constant temperature and pressure system, will be the first step to define what we mean by chemical equilibrium. And it will be the first step, actually, to find the composition of equilibrium, okay, of a chemical system. But before we do that, we have to introduce the concept of chemical reaction. So I hope it's not too vague, okay? Again, these are let's say, concepts that not necessarily you will need to learn for the exam, but it's something that you actually do need to absorb, okay? The fact that there are several forms of the equilibrium conditions, and you can manipulate those to find a condition that suits you, okay, using the right chemical potential. And okay, but for the rest of the course, we're going to be using just Gibbs energy, of course. So later on, you get used to these, okay? So these fast lessons don't really allow us to go too much into the details. I'll stop recording